Hi everyone. Today I should be picking up where Anthea left off. And so she did combustion of hydrocarbons, so I should be looking at functional groups and alkyl halides. However, I think it's important that we first have a little bit of a look at the bonding that goes on in organic substances, because as we look at each of these different types of organic substances, we talk about how soluble they are and what their boiling point is and things like that. And you're not going to be able to make any sense of that if we don't talk about why they have specific boiling points and solubility. And that all comes down to the type of bonding. So we know that organic substances are bonded covalently. We know that there are molecules with van der Waals forces, I suppose, in between the molecules. So we touched on that in physical sciences, but we really didn't go into much detail about what a van der Waals force is, okay? We also had a little bit of a look at polar bonding in water, but we didn't go into much detail there either. So I would like to explain what a van der Waals force really is, what polar bonding really is, so that then you can understand how it gives these different compounds these different physical properties like boiling points and solubility. So it's a fairly complex topic. So bear with me. I'm going to try and be as clear as possible, and hopefully it makes sense. All right, so the first thing I'm going to talk about is, I think I'm going to talk about van der Waals forces first. Okay, so what is a van der Waals force? Well, we know that, let's say methane. Yeah, let's go with methane. Looks like this. Okay, and we know that these lines that I've drawn, they are covalent bonds. And we know that what they really are is the sharing of electrons, yeah? So in here, we don't really have a line, obviously. We've got two electrons being shared, okay? Now, the electrons don't just sit in one spot and stay there nicely. They're constantly moving around, okay? So they might kind of shift over here, and then they might kind of shift back over this way, that kind of thing. So the electrons are constantly moving around. Now, what happens is if at some moment the electrons shift, let's say closer to the carbon. So electrons are negative, so the negativity there is closer to the carbon, which means that the hydrogen is slightly positive, I suppose, relative to the carbon, just for a moment, because the electrons are constantly moving around, okay? If that happens and we get sort of a slightly positive charge here, then that's going to align with a negative charge somewhere on a neighbouring methane, okay? So that's what a van der Waals force is. I'm going to write some notes and I'm going to show you a little clip because I highly doubt that you've just fully understood that and know what's going on. So, another name for a van der Waals force is a dispersion force. So we call that dispersion forces. That's our van der Waals force. You might also see it referred to as a London dispersion force. So don't be alarmed if you see that wording, London dispersion force. It's all the same thing. It all just means van der Waals forces. And what happens in what happens in a dispersion force. Okay, so we get what we call a temporary dipole. So a temporary dipole is what I've illustrated here, where temporarily we've got a sort of relatively positive here and relatively negative here because of where the electrons are sitting at that moment. So the dipole is sort of is the relative positive and negative aspect. Okay, so it's where you've got a relative positive and negative bit there. So we have a temporary dipole here. Okay. Now, what happens with the temporary dipole is if we have a partial positive charge here, okay, that's not hydrogen ion, that's a partial positive charge, okay, then that might induce a negative charge on a neighbouring molecule, okay? I'm going to write that down and then we're going to have a little look at a clip that kind of explains that. So, temporary dipoles induce dipoles. Temporary dipoles induce dipoles. So what that means is what I've said, probably not very clearly, and I am sorry. Electrons may be momentarily distributed unevenly within the molecules, inducing a temporary dipole. Then neighbouring molecules with similar temporary dipoles are attracted weakly to each other. Okay, I've got a little video here. This one here, temporary dipole example with helium. So this example is looking at the van der Waals forces in helium when helium's kind of compressed and pushed to, like when the atoms of helium are sort of pushed together, there's little van der Waals forces between them. And so it's showing this with helium because it's a little bit easier to demonstrate it with one atom rather than a molecule with 5 atoms.
And so let's look at it. Why are London dispersion forces important? Well, they're in everything. And if it weren't for them, we'd never have noble gases in a liquid phase. And we know we can do that if we can cool it down. And so what holds helium together when it gets into this liquid phase is going to be these London dispersion forces. So right here I have 2 helium atoms, and so they're going to have 2 protons on the inside, 2 electrons on the outside. And so as we move them close together, watch what happens to their electrons. Let's watch that again. As they move close together, the electrons are going to migrate. What's doing that? Well, the electrons on the outside of one helium are going to be attracted, just Coulomb's law, to the protons on the inside of that other helium. There's also going to be repulsion between those electrons on the outside. And so what this really is creating are 2 what are called temporary dipoles. They have positive and negative ends. And so a London dispersion force is simply going to be the connection between those 2. It's fairly simple. It's going to hold them together. Now it's just instantaneous, it's temporary, and then it's going to go away. But if we have enough of these atoms in an area and it's cool enough, then we can get that. So what's going to increase these London dispersion forces? Well, contact area is one thing. The more...
Fantastic. I really like that explanation and the image. I think that sums it up perfectly. That is a van der Waals force, okay, a London dispersion force. We just call them dispersion forces or van der Waals forces in this course. I also like that you've probably got my face in the bottom right corner instead of the guy's face who's actually explaining the concept. So I hope you've enjoyed that aspect. The video is going to go on and talk about what affects the size of these forces. We don't need to know all of that in too much detail. I'm just going to explain it at a very basic level with our alkanes. So if we look at the difference between, let's say, ethane and hexane, ethane is CH3, CH3, okay? okay? So if that bonds with the van der Waals forces to another ethane, I mean, those bonds are sort of in here somewhere, okay? So there's minimal points of contact there for the van der Waals forces to exist. Whereas if we look at hexane, now if we have another hexane to go with that, there's much more points of contact. Now we can get van der Waals forces all along there. Okay, so that means that the bonding between hexane molecules is stronger than the bonding between ethane molecules. That means that hexane is going to have a higher melting and boiling point, okay? And that is why methane, ethane, propane, and butane, and this little table is on page 4 of your organic chemistry booklet, those are all gases at room temperature because the bonds between the molecules aren't very strong because there's not a lot of contact area. Whereas from pentane onwards, they are liquids. Those bonds are stronger, so the molecules are closer together, so they are in liquid form at room temperature. Okay, so there you have van der Waals forces. There are some really great videos on YouTube. If you're really struggling with this concept, then I suggest you have a look on there for more videos. It's good to look at the videos where they sort of have little animations and things. So that might help if you feel you need it. The next thing I want to talk about is the difference between that and polar bonding. So we talked about polar bonding in physical sciences, but we only talked about it in terms of water. So I'm going to recap that first. Oh, I keep forgetting I can use my keyboard if I want to. How exciting. Polar bonding. Okay, so polar bonding in water, what does that look like? Well, water is not symmetrical. Okay, so what does a water molecule look like? Well, we've got our oxygen in the middle. Okay, and then we've got a hydrogen here and a hydrogen here with about 60 degrees in between. Okay, and again, these lines are really the sharing of electrons. So in here we have the sharing of electrons, don't we? Okay, now these electrons, they do still move around, but they're more attracted to the oxygen than the hydrogen. Why might this be? Is anyone thinking about it? Think about it. Why would they be more attracted to the oxygen than the hydrogen? I'll tell you. I had to think about it for a second myself. Okay, oxygen has 8 protons, and hydrogen only has 1. So oxygen has much more attraction for the negative electrons because its nucleus is much, much more positive. Another way of saying this is to say that oxygen is much more electronegative than hydrogen. Okay. Okay, so that brings in this concept of electronegativity, which is something you need to know about, and it is how well something is going to attract electrons. So you might like to have a little look at your periodic table and think about which atoms are going to be more electronegative. Which atoms in the periodic table do you think are going to be the best at attracting electrons? If you want to think about it, you might like to pause. Well, One that is really, really, really electronegative is fluorine. This makes sense because fluorine only has 2 electron shells. So the valence electron, where the electrons are attracted to, is much closer to the nucleus, okay? And fluorine, of course, has 9 protons, which is much more than, say, lithium. So let's have a little look at at the electronegativity of the elements in the periodic table. Okay, so as you can see here, fluorine is the most electronegative. They've even been assigned values for their electronegativity, and they've also put colours in here to make it more helpful. Now, it makes sense that the metals aren't very electronegative. They don't attract electrons. They ditch their electrons, don't they? Whereas the non-metals are relatively more electronegative. So we might say that something like hydrogen is electropositive compared to, say, fluorine, which is very electronegative. Okay, so if we look at the difference between oxygen and hydrogen, which are our 2 elements that we have in water, there's a big difference in electronegativity there. So 2.1 compared to 3.5, there's a big difference in electronegativity. So that's why the electrons sit much closer to the oxygen. And what that does is it gives the oxygen side of the molecule a partial negative charge, not a full negative charge like in an ionic bond, just a partial negative charge because the electrons are closer. To write partial negative, we do this symbol here, okay? And the other end of the molecule, the hydrogens, have a partial positive charge. That means that when we introduce other water molecules, the partial positive end is attracted to the partial negative end. So that looks like this. Let's have a little look at the polar bonds. So let's say we have a water here. Okay, and this is partially negative, this is partially positive, that's also partially positive. And let's say we have another water molecule neighbouring it. Partially negative, partially positive, partially positive. A partial negative charge between oxygen and hydrogen here is going to create a bond. And the same thing is going to occur here. Now this is much, much stronger than a van der Waals force because those electrons are always closer to the oxygen. They're not moving around and sometimes closer to the oxygen and sometimes closer to the hydrogen. So it's not a temporary dipole, it's a permanent dipole. Okay, so I've just made some notes on what I just said so that you've got something in writing. So polar bonding is when there is a significant difference in electronegativity. There are permanent dipoles. The partial positive charge on one molecule is electrostatically attracted to the partial negative charge on a neighbouring molecule. Therefore, these are stronger than dispersion forces. Okay, so that is polar bonding, which is different to van der Waals forces. It's just a stronger version of a van der Waals force. Now this is it can be a fairly complicated concept. It can get quite complicated. In terms of what you need to know for the course is you need to know that whether you have a polar bond or not depends on the difference in electronegativity between the 2 atoms involved in the molecule. And we're going to teach you which types of organic compounds are polar and which types aren't polar. And it might seem a little bit confusing at times. To try and make it make a little bit more sense, I'm going to teach you something that's just slightly outside the scope of the course because I feel that you might have questions if I don't talk about this. So another thing that comes into play as to whether it is polar or just a regular van der Waals force is symmetry, okay? So let's have a little look at carbon dioxide. Carbon dioxide is like this, okay, in a straight line, 180 degrees between the oxygen atoms. Okay, so while there is a significant difference in the electronegativity between carbon and oxygen, let's just have a look. Carbon and oxygen, so there's an electronegativity difference of 1, which is fairly significant. By the way, the numbers for electronegativity are also not in the course. You don't need to know the numbers. We look at it more just like there is a big difference or there is not a big difference. We teach it a little bit black and white for the sake of this course, but of course it's a grayscale. Anyway, this is in a straight line, okay? So which one is more electronegative? Oxygen is, because it's got more protons. So that means that the electrons are going to sit closer to here and the electrons are going to sit closer to here. So you might think that this creates a permanent dipole. So because this is symmetrical, we've got a partial negative charge on both ends, they sort of cancel each other out, okay? It sort of all gets cancelled out. That means that carbon dioxide is non-polar and it is a gas at room temperature. The difference with water is the 60-degree angle, okay? So it means that we've got our positive bits at one end of the molecule and our negative bits at the other end of the molecule. So that's why something like water is polar and something like carbon dioxide is non-polar. So this will come up a little bit as we look at the various functional groups in organic chemistry. So again, I've added a note here to explain, just so that you got it written down, what I just said. It's not in the course. If you don't understand this, it's not the end of the world. I just feel that understanding it may help some of you. Stupid emails. So not in the course, but if the same atom is evenly spread around the molecule, like oxygen is here, its electron density is evenly spread across the surface. Okay, so the partial negative charge cancels out effectively. Molecules can only be polar if the density is asymmetrical, where we've got most of our electron density up here and not so much down here, like in water. Okay, hopefully this is making sense so far. All right, now our strongest type of polar bond we call a hydrogen bond. The bonding in water, I suppose, is technically hydrogen bonding rather than polar bonding, but a hydrogen bond is just a type of polar bond. The reason that hydrogen bonding is stronger is because hydrogen is relatively electropositive. So when you pair it with something that's quite electronegative, like oxygen or nitrogen, for example, which it's often paired with, there's a big difference in electronegativity. So that creates stronger bonds between the molecules. So I've made a little note again. Hydrogen bonding is a stronger form of polar bonding. Hydrogen is relatively electropositive, so when it is paired with something fairly electronegative, e.g. oxygen or nitrogen are often bonded to hydrogen, it creates an even stronger polar bond, which we call a hydrogen bond. Therefore, molecules that contain hydrogen bonding have even greater boiling points than other molecules. Okay, I now need to talk a little bit about solubility, which all this bonding stuff is related to solubility, but it just brings another little layer of complexity in. So polar substances are soluble in other polar substances. So if you have something that is polar, you're going to be able to dissolve that in water. It's soluble in water. Non-polar substances are soluble in other non-polar substances. So it's because the bonding is similar. So if we take something polar, we can dissolve it in water and it'll be soluble because it creates those same polar bonds with the water itself, because they're both capable of creating polar bonds. Whereas if I take something that is non-polar and I try and dissolve it in water, which is polar, we're not going to get polar bonds being formed because one of those things is non-polar. Okay, so that's what solubility is. It's the bonds being formed between the water, or whatever the solute might be, and whatever you're adding in. Okay, now mostly when we talk about solubility, we talk about solubility in water, which of course is polar. So if we know something's polar, we know that it's going to be able to dissolve in water. I'd like to look at an example now. The example that I want to look at is an alkyl halide. Alkyl halides. So what is an alkyl halide? It is a carbon compound that has a halogen. So fluorine, chlorine, bromine, iodine, for example. Let's have a look at one of them. Let's have a look at bromo. No, I like fluorine the best. Let's have a look at fluoromethane. Fluoromethane looks like this. Okay. Now suddenly this isn't symmetrical like methane is, because one end has fluorine, which is ridiculously electronegative, and the other end has hydrogen, which is ridiculously, okay, not ridiculously, relatively electropositive, okay? So we're going to get a partial negative charge on the fluorine, okay? We're going to get partial negative there and partial positive here. Now you don't need to know about the symmetry because it's not in the course, as I said earlier, but you can just think of it as there's a big enough difference in electronegativity between carbon and fluorine. But basically the end of the molecule with all the carbons and the hydrogens is going to be relatively electropositive, and the fluorine is the electronegative part. So that enables it to form polar bonds with other molecules of the same, okay? And in fact, it can form polar bonds with other polar molecules, like water, okay? So what happens when we mix this in water? Well, it creates polar bonds with the water, because we have our water. Let me just think about how I'm going to draw this. So when we mix this into the water, and this is, I should have typed this, solubility. I'm going to type it. Okay, so if we're to put some of this in water, we've got CH3, stupid pen, I have to press down quite hard today, and we've got our fluorine, so electronegative, partial negative charge, partial positive charge. Now, when this comes into the contact with water, it's able to form these polar bonds like so. We might have our oxygen line up here, which, as we know, is partially negative. Therefore, we get a polar bond there. And then we might have, you know, one of our hydrogens, polar bond there. Oh, H+. It's not H+, that makes it a hydrogen ion, which is ridiculous. Okay, so it is soluble because it's able to create polar bonds. Something like methane is not going to be soluble in water because it doesn't have polar bonds. It can't create that bonding with the water. So the water sort of stays bonded with itself and the methane stays bonded with itself, and it looks a little bit like mixing oil and water together. Okay, except of course that methane is a gas, but anyway, that's the concept. Okay, so what we've discussed is fairly complex, and I've possibly gone into more detail than what you would need to on an exam, but the types of answers that you have to give in terms of bonding, boiling points and solubility, you'll see modelled as we go through different problems throughout organic chemistry. I just sort of wanted to teach you the concept so that when we teach you about different organic compounds, it makes more sense. Now, functional groups. What is a functional group? Well, it's written out pretty clearly here. an atom or group of atoms that determines the chemical properties of an organic compound is called a functional group. So we just have our normal alkanes, but then if we've got something special going on, like if you chuck a nitrogen on there with some hydrogens, that's a functional group because it changes its properties. Now, the different functional groups that we're going to look at, Anthea and I are going to go through each of them, and they're on your formula sheet here: alcohols, aldehydes, carboxylic acids, ketones, esters, amines, amides, and alkyl halides. The first one that I'm going to look at quickly with you now is the alkyl halides, because they're fairly straightforward and you've already looked at them in physical sciences. So, why do alkyl halides have higher melting and boiling points than the corresponding alkane? Because they have an they have a partial negative charge on one end, so they can create polar bonds. Now, this next bit is going to seem like the opposite of what I've told you, which it kind of is, but I'm going to need to explain why. Most are liquids which are insoluble in water. Okay, something like fluoromethane is going to be soluble in water. But something with a much longer carbon chain, like fluorohexane, is probably going to be insoluble in water because we've got okay, I've just done fluoropentane because I ran out of spaces for the carbons or whatever. But we've got this whole section here, which is non-polar, and it's a big section. There's only one little bit at the end that's polar. So it's a little bit soluble in water, but generally it's not very soluble in water because most of it is a non-polar carbon chain. Okay, so only the ones with really small carbon chains are going to be soluble in water. Okay, generally they're soluble in typical organic solvents. Organic solvents are non-polar, and most of our alkyl halide is non-polar. So this part is non-polar. This part is polar. Okay, because most of it's non-polar, it dissolves well in non-polar substances, and it doesn't dissolve very well in polar substances like water. So it's not very soluble in water unless it's just like fluoromethane. Okay. Next, chemical properties. Okay, can be prepared by reaction of hydrocarbons with halogens. We know this. So one way to make a hydrocarbon is to do a substitution or an addition reaction with an alkane or an alkene. So you've done this to death. This draw the equation for the reaction between propene and hydrogen chloride. Propene looks like this. And we're mixing that with hydrogen chloride, HCl. Hydrogen chloride as a gas is called hydrogen chloride, not hydrochloric acid. It's only an acid if it's dissolved, if it's like aqueous. All right, and what do we get? Well, it's going to break that double bond, as you would know, and we get the chlorine on one of the double bonds. So the possible organic products, there's two different ones because the chlorine could attach to the middle carbon or the end carbon. So we can get it here. And I wish I could use different colors, but Microsoft Edge is only letting me use blue now. And the other possible product would be to have the chlorine on that carbon. Now, one of these is much more common than the other, but it's not in the course, and off the top of my head, I can't remember which one it is. All right, so that's that. Of course, you haven't learnt about alcohols, so this is a little bit weird, but what an alcohol is an organic compound with an OH group in it, which Anthea is going to go over next lesson. So we're looking at ethanol, which you, of course, wouldn't know what ethanol is, so I'm just going to tell you, take my word for it. Ethanol is ethane, except we've got an OH group instead of a hydrogen. Hydrochloric acid is a hydrogen halide because it's hydrogen and a halogen. Of course, that's HCl. And what happens is the OH swaps with the chlorine. So we get our chlorine there. So now we have this OH here and this hydrogen here, which of course, what do you get when you've got two hydrogens and an oxygen? Water. It says to name the organic product, that is chloroethane. No numbers required because there's no such thing as 2-chloroethane. Another property of alkyl halides is that they will react with a strong base to form alcohols, which again, we haven't covered alcohols. That's next lesson, but let's have a look at what that looks like anyway. So let's look at, I'm going to do 2-bromopropane. Okay, we'll react that with a strong base, like sodium bromide. No, don't hate me. Sodium hydroxide, thank you. More like, so what happens is the bromine swaps with the hydroxide because it's nice for sodium bromide to be a thing, a nice ionic salt. And so that gives us an alcohol and our salt. So that is that. Now, if you found this lesson super confusing, that's because this is a really confusing concept and not because I am a bad teacher, I'm pretty sure. You may have lots of questions for me this lesson, so feel free to ask me those. I hope this video isn't too long. I have to go through and edit it and delete heaps of bits where I forgot what I was talking about. There aren't really problems for you to do because mostly I explained concepts to you. So, I mean, I don't really think you need to do problems this lesson because all I would really set for you is addition and substitution reactions. So if you feel like you need practice with addition and substitution reactions, then by all means do some of those. If you can't find them anywhere, then ask me and I'll get you some. But it's probably been a pretty long lesson anyway, so now might be the time for you to ask me things that you haven't understood. Also, you should be aware that the level of detail that I've gone into is more than what's required, but if I don't go into that level of detail, then not much makes sense and a lot of things seem to, what's the word I'm looking for? Be like when there's one thing that means something and then another thing that opposes that thing. What is it? Not counterintuitive. Is it counter something? I don't know. Maybe you know. But anyway, I'm sure that's a really helpful end to the video for you. And that's it. I've had enough. I'm sick of it. So that's it. Thank you. Goodbye.